Hello students, welcome to Marine Engineering Tutorials. I am Atul Kumar Gupta and back with a new tutorial. We are presently studying marine boilers. In this lecture, we will go through the following topics. First, we will look at the internal energy of steam followed by the different phases of steam. Next, we will explore how saturated steam temperature relates to its pressure. After that, we will see various steam pressures used for shipboard applications. Then we will discuss the methods of improving steam plant efficiency. Finally, we will compare steam heating with power generation applications on ships. Let's go through these one by one in the next slides. Total internal energy of steam. This diagram illustrates the total internal energy of steam, also referred to as specific enthalpy. It is the sum of the sensible heat of water, the latent heat of evaporation, and the sensible heat of steam due to superheating. We can observe that 419 kilojoule of sensible heat is added to each kilogram of water when it is heated from 0 degrees Celsius to 100 degrees Celsius at atmospheric pressure. When 1 kg of water is evaporated at atmospheric pressure, its temperature remains at 100 degrees Celsius. The steam produced absorbs 2256 kilojoule as latent heat, resulting in a specific enthalpy of 2675 kilojoule. If saturated steam at 100 degrees Celsius is further heated to 200 degrees Celsius, it absorbs an additional 200 kilojoule of sensible heat, raising its specific enthalpy to 2875 kilojoule. It is evident that the latent heat component in steam is much larger than the sensible heat component. Phases of steam. This sketch illustrates the different phases of steam on a temperature entropy diagram, where temperature is plotted on the ordinate or vertical axis and specific entropy on the abscissa or horizontal axis. In a boiler, water is supplied to the steam drum along the saturated liquid line, either with or without preheating. Inside the boiler, water absorbs latent heat and leaves as saturated steam along the saturated vapor line. Within the dome-shaped curve bounded by the saturated liquid line and the saturated vapor line, steam exists as a wet mixture of water and vapor. The tip of the curve represents the critical point which corresponds to a temperature of 374 degrees Celsius at a pressure of 220.6 bar. Below the critical point line, Water exists as a subcooled liquid to the left of the saturated liquid line. Saturated stream can be superheated beyond the saturated vapor line but still below the critical point. Operation of steam in this region is referred to as boiler operation. When steam is produced above the critical point, the equipment is termed as a steam generator rather than a boiler. Many modern thermal power plants operate with supercritical steam, typically at pressure above 250 bar. In such plants, the feed water is completely converted into the steam within the heat exchanger, and there is no drum or separation space for steam and water as in conventional boilers. Relationship between saturated steam temperature and pressure. This diagram shows relationship between the temperature and enthalpy, where absolute pressures are also shown corresponding to the saturated steam temperature. From this diagram, it can be stated that saturated steam temperature increases as the pressure is increased up to the critical point. This thermodynamic relationship between the saturation temperature and the saturation steam pressure is given by Clapeyron equation, which states that the rate of change of saturation pressure with respect to saturated steam temperature is equal to latent heat of vaporization HFG divided by absolute temperature T multiplied by difference between specific volume of vapor and liquid, that is Vg minus Vf. This relationship is not linear and its plot is given on the following slide. This plot shows the variation of saturated steam temperature on the ordinate on linear scale with respect to its saturation pressure on the abscissa on the log scale. Selection of steam pressure. This table describes important steam pressures used on the ships. The data at atmospheric pressure is provided for comparison only. The specific enthalpy of saturated steam is 2675 kilojoule per kg, consisting of 419 kilojoule per kg of sensible heat of water and 2256 kilojoule per kg of latent heat. When steam is superheated to 500 degrees Celsius, it gains an additional 813 kilojoule per kg of sensible heat, giving a total enthalpy of 3489 kilojoule per kg. A steam pressure of 4.5 bar has traditionally been used for heating fuel oil to 145 degrees Celsius, corresponding to a viscosity of 15 cst. However, newer ships may use 3 bar steam pressure to maintain fuel oil temperatures between 85 to 100 degrees Celsius due to improvement in fuel quality. The specific enthalpy of saturated steam at 4.5 bar is 2752 kilojoule, inclusive of 650 kilojoule per kg sensible heat and 2102 kilojoule per kg latent heat. When superheated to 500 degrees Celsius, it receives 732 kilojoule per kg of additional sensible heat, giving a total enthalpy of 3484 kilojoule per kg. A steam pressure of 9.5 bar is maintained for heating cargo oil on conventional oil tankers. It is also used for air ejection from vacuum condensers, operation of stripping pumps, and tank cleaning operations. The specific enthalpy of saturated steam at this pressure is 2775 kilojoule, inclusive of 761 kilojoule per kg sensible heat and 2014 kilojoule per kg of latent heat. When superheated to 500 degrees Celsius, it gains an additional 703 kilojoule per kg of sensible heat, giving a total enthalpy of 3478 kilojoule. A steam pressure of 16 bar is maintained on conventional oil tankers for operating cargo pump turbines. The primary purpose of using higher pressure is to provide superheated steam at the turbine operating pressure of 9.5 bar without the need for a conventional superheater. This is achieved by throttling 16 bar steam to 9.5 bar, which theoretically provides a superheat of 22.3 degree Celsius. The specific enthalpy of saturated steam at 16 bar is 2795 kilojoule per kg, inclusive of 854 kilojoule per kg sensible heat and 1941 kilojoule per kg latent heat. When superheated to 500 degrees Celsius, it gains an additional 675 kilojoule per kg of sensible heat, resulting in a total enthalpy of 3471 kilojoule per kg. Although the maximum attainable steam pressure is 220.6 bar at the critical point, such high pressures are impractical. For propulsion, steamships typically use pressures in the range of 56 to 110 bar. At 100 bar steam pressures, the specific enthalpy of saturated steam is 2724 kilojoule, inclusive of 783 kilojoule per kg sensible heat and 1941 kilojoule per kg of latent heat. When superheated to 500 degrees Celsius, it gains an additional 650 kilojoule per kg of sensible heat, giving a total enthalpy of 3374 kilojoule per kg. It can be observed that the latent heat of vaporization and the sensible heat of superheat both decrease as steam pressure increases. A pressure of minus 0.96 bar or 95% vacuum is maintained in the condenser to maximize the recovery of sensible heat in the steam turbines, thereby improving steam plant efficiency. The specific enthalpy of saturated steam is 2562 kilojoule per kg, consisting of 138 kilojoule per kg of sensible heat of water and 2424 kilojoule per kg of latent heat. However, all the latent heat of steam is rejected in the condenser, which is the main reason for the relatively low efficiency of steam power plants. Improving steam plant efficiency. This diagram illustrates the method of improving steam plant efficiency by using superheated steam at high pressure and exhausting it at the lowest possible pressure. Additional measures such as steam reheating are also employed in large steam plants. Saturated steam at 100 bar is superheated to 500 degrees Celsius along line BC, where 650 kilojoule per kg of heat is added, raising its total enthalpy to 3374 kilojoule per kg. If the steam is exhausted to an atmospheric condenser along line CD, the heat utilized in the turbine, represented by line DE, amounts to 699 kilojoule per kg. Alternatively, if the steam is exhausted to a vacuum condenser along line CF, the heat utilized in the turbine, represented by line FG, increases to 813 kilojoule per kg. Thus, when steam is exhausted to a condenser maintained under vacuum instead of an atmospheric condenser, the turbine produces 114 kilojoule per kg of additional work, corresponding to a 14% increase in work output. Comparison of steam usage for power generation and heating applications. Type of steam required. Superheated steam is required for producing power, whereas saturated steam is sufficient for heating purposes. Pressure of steam required. High steam pressure is necessary to improve turbine plant efficiency, whereas low pressure steam is adequate for heating applications. Efficiency of plant. The efficiency of steam plant for power generation is relatively low because the latent heat of steam cannot be utilized in the turbine and is instead wasted in condenser. Nevertheless, about 90% of the world's electricity generated using steam power plants, primarily because coal, a cheap fuel, is widely available for land-based plants. However, coal is unsuitable for ships due to handling difficulties. Until recently, steam propulsion at sea was largely restricted to natural gas carriers, as they could conveniently utilize boil off natural gas as fuel. With the development of dual fuel engines, steamships are now losing their popularity on gas carriers too. In heating applications, to utilize the maximum latent heat of steam, a steam trap, a special type of valve is used, which allows only condensate to leave the heater. A faulty steam trap reduces the heating capacity of the system. ease of use. Both power and heating applications of steam require system warming before operation. A heating line can be warmed up quickly, but warming up a turbine requires considerably more time and effort. Maintenance required. Heating is a static operation and generally maintenance free, though repairing a leaking heating coil is difficult and poses the risk of contamination of boiler water. Steam turbine operation requires little maintenance and is simpler compared to diesel engines. This completes our study of internal energy of steam, phases of steam, relationship between saturated steam temperature and pressure, selection of steam pressure for shipboard use, methods for improving steam plant efficiency, and comparison of steam heating and power generation applications on ships. This book has been written by me and covers all the topics as per the Indian Maritime University syllabus. It explains key concepts using simple illustrations. The book also includes answers to all the questions that have appeared in examinations conducted by Indian Maritime University. It will help students prepare effectively for exams and also support them in working safely with ships' boilers. I hope you enjoyed the lecture. Feel free to share your feedback in the comment section. If you found this tutorial helpful, consider sharing it with your friends. Subscribe to the channel to stay updated with upcoming tutorials. I'll be back soon with a new lecture. Thank you for watching till the end.